So let's get started. In today's lecture, we will be talking about a very important topic, that is Bayesian networks. So we can say that actually now we are starting the main topic, that is reasoning under uncertainty. The previous two lectures that we have covered, that was the foundation, or we can say the prerequisites of these topics that we are going to start today onwards. Okay, so let's get started. This Bayesian networks. So what it is actually, so let's talk about it. Good evening, Abhas. So till the previous lectures, we talked about the basics of probability. We talked about what is marginal probability, conditional probability, joint probability, law of total probability, Bayes theorem, right? All these topics we discussed in the till the previous lecture, right? And I also talked about what is independence, what is absolute independence, what is you can say the conditional independence. We also talked about joint probability distribution, right? So we set the foundation that first we need the joint probability distribution. That is very important. That can answer any question related to a domain, right? And then we discussed that it is consuming a lot of space and time complexity is also very high. So what we figure out that we can use the concept of independence. So by using the concept of independence, we reduced it. You can say space required to store all the variables, we reduced it somehow. And then we used the concept of conditional independence, because we know that there will not be the case that every time all the random variables are having absolute independence. So we introduced the concept of conditional independence concept. We figure out how we can use the joint probability distribution as well, and now we don't have to store a lot of variables. Yes or no? So that was the quick overview of what we have discussed. So I wanted to discuss this, just I wanted to give you a quick recap of what we have covered, so that we can now relate it to this Bayesian network. Okay, so let's get started. So carefully, what is actually Bayesian network? So Bayesian network are a knowledge representation formalism for reasoning under uncertainty. So basically this also represents the knowledge. This also represents the relation between various random variables. We will see that. A Bayesian network is a directed acyclic graph. If you don't know what is directed acyclic graph, no need to worry about it. I will be covering that also in brief. So directed acyclic graph that encodes assumptions of conditional independence. So now using that directed acyclic graph, that will represent the conditional independence also. We will get to know what variables or which variables are conditionally independent of each other. So we will see that also. Important that Bayesian network is a directed acyclic graph. In a Bayesian network, nodes are stochastic variables. What are stochastic variables? Stochastic variables are nothing but the random variables that we have, right? So all the nodes that we are going to have in the Bayesian network are going to be your nodes, okay, are to be your random variables only. And arcs, that means the edges between the nodes, represent the dependency between the nodes. What else? Bayesian networks would explicitly encode deep knowledge rather than heuristics to simplify knowledge acquisition, provide a firmer theoretical ground, and force use. So we will see how we can use this Bayesian network to answer any question that we have. Fine. Before even starting about what is Bayesian network actually, let's talk about a few terminologies that we have, like trees and graphs. Okay, so what is a graph? Sachin sir will be covering a graph in lot of detail, okay, in the graph theory also, and also when we talk about in this AI subject, when we talk about the search, right? Uninformed search, informed search, adversarial search. So there also he will talk about a lot in detail about graphs. We will see what we need to understand this Bayesian network in detail. Okay, I will cover all those things so that you can understand clearly. A graph or a network, basically we can represent a graph, let's say by G, and it is having what? It is having n comma L, where n represents the nodes and L represents the arcs, or you can say edges also. Clear? So of, so we are having E and so on, and we also call nodes as vertices. And what about edges? A set L of nodes are there. Now set L is a subset of all possible pairs of nodes in. Now let's talk about this particular graph given to us. First of all, if I ask you what are the nodes present in this first graph, so you will say that we have A, B, and C. These are the nodes, these are the vertices that we have, right? Now if you focus on the edges, so you will find that there are edges. So there are the edges that we are going to have, we are having is directed edges, right? There is direction indicated, we have a edge. Similarly from C to B, similarly from B to A also we have one edge, right? So these are the set of edges. That means A comma C, then we have B comma C. So A comma C is there, B comma C is there, you can write like this, or B comma A is also there, right? Similarly for this one, we have edge between A and C, we have edge between B and C. So that's what we have written, right? And similarly here also, this is undirected graph. There is no direction represented by the edges. So now we can have direction from A comma C, or we can have we can say there is a possible path that we have between these two vertices A and C. So A is there, B comma B is there, and A comma B is also there. Is this clear? Am I clearly audible or not? Is there any lag, Manjunath, from your side also, or are you facing some lag? Just let me know. Okay. Is it fine now? Okay, thank you. Fine. So it's okay. I mean that I cannot do much about the lag, even if it is there. So just you can let me know whenever you face any lag. Just let me know. I will pause for a moment, and then when it is fine, I will continue. Okay, this thing we can do. Fine. Okay. So you can see these are the edges that we have. Right, and here in this first one, if you see, it should be C comma B, right? Like if I'm talking about the directed edge, so it should be B comma C, should be C comma B. If in the undirected we are writing all possible pairs like A comma C, C comma A, B comma C, C comma B, A comma B, B comma A, in that, okay, but that is fine. It's fine. So this is what we have as graph. Now there are certain types of graph that we have. Two categories of graph. One is directed and other one is undirected. When I say undirected, that means there is no direction in the edges. So if you see this particular graph, you can see in every edge there is no particular direction from where to where we have to go. But if I talk about the directed, now there is a further categorization in the directed graph, that is connected graph and disconnected graph. Okay, if you see disconnected graph, you can see this node or vertex C is not connected to the other component of the graph, right? Disconnected graph. Similarly, further if I go in disconnected graph, there is acyclic graph, there is cyclic graph. When I say cyclic graph, so you will find that there is a cycle present in that graph. So from B to E you can go, then from E to D, then that again back to B you can go. So there is a cycle present over here, right? There's a cycle present over here. So this is a cyclic graph. Now let's focus on this acyclic graph. In acyclic graph, we can have single connected. That means there is only one component, and there can be multiply connected also. So multiply connected, that means you can see there is an edge from C to E also. Like E is this vertex E is connected to B also and is connected to C also, right? But if you see single connected tree, that means again there can have further categorization, simple tree and polytree. So polytree, you can see that there is no edge from A to C, but there is a edge from C to E also, right? That means it is single connected. It is single connected. And if you see simple, so a usual tree that we have from A, it is having two child here, then B is also having two child here. So this, it is a simple binary tree, you can say. Okay, is this clear? So these categorization, understand this thing, these categorization is not important for you. Okay, just you need to understand what is directed acyclic graph. What is a directed acyclic graph? Now, can I say good evening, Sneha. If I'm, let's say, I'm talking about this tree. Let's say we have this something like this. Can I say this is a directed acyclic graph? Is it a DAG? What do you say? Is it a DAG? The answer is yes. Yes, right? Because there is all the edges are directed, right? So, and what else? There is no cycle. So A stands for acyclic. That means there is no cycle present over here. Okay. Now, if I ask you this thing, let's say, is it a directed acyclic graph? Here the answer is yes. Here the answer is no. It is not a directed acyclic graph. Why? What is the reason? You will see that this is directed graph, but this is not acyclic. Why? Because there is a cycle present over here. If you go from B to D, then D to C, then again you can come back to B, right? So there is a cycle present over here. There is a cycle present over here. So in Bayesian network, for Bayesian network, we use DAGs. We use DAGs, that is directed acyclic graph. And like you will see this topic in graphs. So if I ask you a topological order, can you answer a topological order? Can you tell me the topological order of this graph? Do you know what is topological order? So you can write topological order. How you can write topological order? So basically you have to start from that vertex. You can start from that vertex which is not having any incoming edge. So if you see, A is not having any incoming edge, right? B is having incoming edge, C is having incoming edge. So you can write A. You can start with, yeah, or other words you can say less degree, but it is important that mainly we start from that. We can start from that vertex which is having not any incoming edge, right? And so here you can write this. So first you can consider A. So now you have written A. So you can consider like this. See, directly also you can write, but this is a method you can follow, that you can just, once you write A in the topological order, you can ignore this. That means these edges are also not present here. Now you have two choices. Either you can consider B or you can consider C. So if you consider B first, then you can have C here. Or if you consider C first, then you can have B here. So can I say these are the two possible topological order of this given graph? Yes or no? Okay. So that thing also will be covered in the graph theory. Okay. So no need to worry about it. But this topological thing is used in multiple subjects. Okay. Fine. So this is the theory of graph that we have. And again, this slide is all talking about what is directed graph, what is undirected graph. So I will suggest you to just give it a read later on. This is not very important for this topic. You just need to understand what is directed acyclic graph. Similarly, just read this about what is parent. So I can say, see, if there is a graph like this, or let's consider this graph only. Can I say A is the parent of both B and C? Yes or no? Right? B and C are the child of A. So we can say A is a parent of B and C both. Clear? Yes. Difference between ancestor and child. It is mentioned over here also. You can read it. Let's read the definitions again. Parent is what? A is a parent of B if directed link from A to B. So that is we can say A is a parent. What about family? The set made up by a node and its parents. So if you consider all those sets, right? So we can consider basically parent and child. If you consider both, we can call it them as family. That set we can call it as family. What about ancestor? A is ancestor of B if exists a path from A to B. Now here you don't have to, you don't need, or it is not mandatory that there should be a directed link, because it is talking about just a path. There should exist a path between those two vertices. Then you can say A is ancestor of B, right? For example, if you see this graph, can I say there is a path between A and B? Yes or no? Can I say there is a path between A and E also? Correct? A and E. So you can go from A to B and then you can go from B to E. So there is a path existing, right? So, and similarly, you can go from A to C and then C to E. So we can say A is ancestor of E also. Clear? So that is the definition of ancestor. And child is simple, right? You can say B is child of A, C is child of A, right? So that is the terminologies. And then again, there are some definitions, and you can just give it a read. These are very simple. Just if you read it once, you will understand. Okay. I don't want to invest a lot of time in these terminologies because these are very simple. Okay. And again, multiple terminologies you will see again in the graphs also. So I'm covering all those things which we really need to understand the Bayesian network. Okay. Similarly, we have a tree also, concept of trees. If every pair of nodes, there is at most one path. Now, carefully see here, in the graph, you can have more than one path also between two nodes. But in case of tree, for every node, every pair of nodes, there is at most one path. Either there is no path or there is maximum one path. So if you can see here, can I say this is a tree? The first one. Can I say this is a tree? Yes. The answer is yes. Why? Because you can see, you can consider every pair of nodes here. There exists at most one path. That means maximum one path is there, either 0 or maximum. What about this one? Yes. Second one. Oh, am I audible? I think I got disconnected. Am I audible now? Okay. What about this one? Is it a tree? Everyone? Can I say this is a tree? Second one. Manjunath is saying no. What is the reason? See, there should exist at most one path. If you carefully see here, E has two parent. But see, nodes can have, if I talk about polytree, nodes can have more than one parent, right? We are not talking about whether it is simple tree or polytree. I'm just simply asking whether it is a tree or not. So if you consider, let's consider all the every pair of nodes, A and B. Can I say there is maximum one path? Yes. A and C, there is zero path. No worries, because we are talking about at most one. Similarly, A and D. Can I say there is maximum one path between A and D? Yes. What about A and E? Yes. What about B and E? Yes. C and E? Yes. B and D? Yes. So can I say this is also a tree? Yes or no? Yes, it is a tree. What about third one? Is it a tree? Now, the third one is not a tree. The third one is not a tree. Why? Because if you consider A and E, there are two paths existing, via B and via C. So this is not a tree. This is not a tree. Clear? But this is a graph, directed graph, you can say. And yeah, there's no cycle also, but yeah, this is a graph. Clear? Fine. So now let's come to our main topic, that is, so now we know what are graphs, what are trees, we know it, right? And we also know what is a directed acyclic graph. That means edges are directed and there is no cycle present in that graph. Okay. And for Bayesian networks, we use directed acyclic graphs. Now let's talk about Bayesian networks. So there are two aspects. One is qualitative. When we talk about Bayesian networks, there are two things that we have. One is qualitative and other one is quantitative. When I say qualitative, that means some dependency, one dependency graph will be there. Like you can see this example. So can I say there is one graph present over here? Yes or no? And this is the directed acyclic graph. Edges are directed and there is no cycle present here. So this is one dependency graph that will be present in the Bayesian network. Okay. Where in that particular graph, we are going to have nodes and edges. And you can say like variables X, a variable having a set. So for example, let's say this is the example of age. A represents age. Now A can have set of states, right? Whether you can say that person is young or person is old. So there are set of states, some set of values that this variable can take. Basically, these are random variables. And a dependency, a edge will be there that represents the dependency. The we will see in detail. So carefully see here, dependency of a variable x on its parent pi, right? Is there any problem with my voice or something? It's fine, right? Okay, Sneha, maybe there is a problem from your side. You can just refresh once. Okay, explain once more. Okay, so I'm saying that when we talk about Bayesian networks, there are two aspects. One is qualitative and other one is quantitative. So if whenever we see a Bayesian network, there will be two things. One is a dependency graph, which we call it as qualitative aspect. Other one will be your quantitative aspect. That means the distribution will be given. We also call it as conditional probability tables. CPT will be given. We also call it as CPT, that is conditional probability tables. Okay. So quantitative, that means this represents the tables. Qualitative represents the graph. In the graph, we have nodes and edges. Edges are directed and nodes are what? Stochastic variables, or you can say simply random variables, nothing else. Random variables can have some set of states, or you can say some set of values. So here, like in this example, A represents age. Now the person can be young or old. So we have these set of states for this particular random variable A. Similarly, if I talk about education, education is another random variable, and we can have here two values, whether education is low or education is high. In this particular example, I'm talking about. Okay, clear? Okay. Now, when we talk about quantitative, so there is a distribution of a variable x given each combination of states pi of its parents pi. So simply what it is saying, that in this CPT, the conditional probability tables, the probability is given. So if any variable is not dependent, if any variable is not conditionally dependent on anything, then simply its probability will be given. For example, let me give you a simple example. Let's say by this example it will be very clear to you. Carefully see this. Let's say there is one disease. Okay, let's say there is one disease, or let me take the example of, let's say, cancer. Okay, so cancer is one disease, and for cancer there will be let's say one test. Let's say some test is there, maybe some x-ray or something is there, right? So x-ray is a test and there is some symptom is there. So let's denote that by just a symptom, right? So now carefully understand this. So this is what? This is a cause, right? And these are the effects. These are the effects, right? And so on. Now, this is a Bayesian network. Now, what this network is representing, now carefully understand this. Here, I can say that X-ray, see, carefully see this. Just answer yes or no. Is there any incoming edge to this random variable cancer? Just answer yes or no. Is there any incoming edge? There is no incoming edge, right? There is no incoming edge to this random variable, that is cancer, right? So if there is no incoming edge, I can clearly say that this is not dependent, or you can say simply this is independent. This is independent. Is this clear? This random variable is independent. Clear? Okay. What else? What else? Carefully see this. When I say this X-ray, is there any incoming edge? Yes, there is incoming edge, that is from cancer to X-ray. So here I can say that X-ray, here I can say that X-ray is conditionally dependent. X-ray is conditionally dependent on cancer. Are you getting this point or not? Okay. Let's say we talk about this symptom. Can I say there is incoming edge to symptom also from cancer? So same thing I can say for this one also, that symptom symptom is conditionally dependent, or conditional dependent on cancer. Are you getting this point or not so far? Is it clear? Crystal clear? Okay. And what can I say about the conditional independence? Do you remember what is conditional independence, everyone? What is conditional independence? So I told you, when, so I can say these two variables, these two effects, or these two random variables are conditional independent given A, right? Exactly. So yeah, in general way, you can say that effects are effects are conditional independent given cause. Effects are conditional independent. Effects are conditional independent given cause, right? So in the previous lecture, if you remember, I discussed the example of toothache, cavity, catch, right? So I told you that when cavity is given, then toothache and catch are conditional independent, and I explained you why it is so, right? So if you have not watched that lecture, please refer that lecture. You will understand what is the meaning of conditional independence. So given the cause, here A is a cause, here A is a cause, I can say effects are conditional independent of each other. So if I talk about the joint probability distribution of A, B, C, how can I write this joint probability distribution? Now I'm discussing the main core of Bayesian network that you are going to use to solve the questions. Carefully see this. So we know one thing, that joint probability distribution can answer any question related to that particular domain. So if I'm writing probability of A, B, C, that means probability of A intersection B intersection C, I can start with the node, or you can say the parent, that is not having any incoming edge, because A is completely independent of anything. So I can write probability of A, I can start with this, multiply. Now let's consider B. I know that B is conditionally dependent on A, so I can write probability of B given A, multiply. What about C? C is also dependent on A, so I can write probability of C given A. This is how we are going to use it. Exactly. B given A, right? Abhas, it should be B given A. Is this clear to all of you? Any doubt, anyone so far? All clear? So this is how we are going to write it. Okay, fine. So that's what I was explaining to you. If you see the formal definition of Bayesian network, see all these slides that I have taken, these are from reputed standard universities like MIT, Stanford, and University of California. So a lot of standard resources I've referred to, just conclude or just take out the crux of this Bayesian network so that you can understand each and everything clearly. So the formal definition, if I talk about of the Bayesian network, so it is let x is a set of random variables, that is x1 comma x2 comma up to xn, that is a set of random variables. And the Bayesian network, a Bayesian network is a directed acyclic graph that specifies a joint distribution. I told you Bayesian network specifies a joint distribution, but how it can specify the joint distribution over X? As a product. Now this is very important, as a product of local conditional distributions. Is this clear? Is this clear to all of you? One for each node. So as you can see, probability of X is equal to X1 up to probability of Xn is equal to Xn is equal to pi of I is equal to 1 up to n probability of xi given its parent variable value. For example, if I told you this, let's say this example, let's consider. Yes, is there any problem, Sneha? I think your network is not, your internet is not working fine. So please refresh or check your internet connectivity. Okay, I think from my side it's working fine. Okay, So now let's see this. Cancer, X-ray, and let's say symptom, or let's generalize this also. I can say, so I'm generalizing this. Let's say disease is there, some disease is there, some test is there, and some symptom is there. Fine. Now carefully see this, everyone. If I simply ask you that what is the joint probability distribution for this one, so you will be writing D comma T comma S, let's say. So you will be saying that it is equal to what? Probability of D, because that is completely independent, multiply probability of T given D, multiply probability of S given D. Fine. Now, if I simply ask you what is the probability, so along with this graph, along with this dependency graph, as I told you, you will be having some tables also, CPT, that is conditional probability tables, by which you can use those values and you can answer it. Okay. So now carefully see this. If I simply ask you a question, find the probability that disease is true, or that disease is present, or I should say disease is true. Yes, that means disease is there, and test is positive, and symptom is present. If someone asks you this question, that disease is true, that the patient that we are talking about is having this disease, find the probability of that. It is also given that the test is positive and the symptom is present. So you are going to use that table here. You are going to use, now let me give you the values also, so that we can solve this, we can make this as an actual question and we can solve this. Let's say the probability of D is given to you, maybe let's say 0.80. This is the probability of D. This is the probability of D. When I say probability of D, that means the disease is true, that is the probability. So can you tell me what is the probability that disease is not true, or the patient is not infected? 1 minus 0.8, yes or no? 1 minus 0.8, so you can find it out from this one. Okay. What now, this is also given to you. Let's say this is also given to you. Carefully say this. Probability, let me just utilize this space. Let me just erase this one. I will be writing it again, okay? Because I have to write a lot of things here. Carefully see this. So I'm talking about this test here. So let's say this is given to you. Probability of test is positive. Probability of test is positive. See, you know one thing. You simply know one thing, that test is conditionally dependent on D. Yes or no? You know this thing, right? How many values are possible here? This thing also we discussed in the previous class. If you remember, I can say that test is positive. The test is positive given that the disease is true. This is one possibility. Yes or no? Similarly, I can also say the test is negative given that the disease is true. Yes. What else? I can also say that test is positive given that disease is false, and test is negative given that disease is false. Is this clear? Can I say these are the possibilities will be there? Now carefully see this, everyone. Carefully see this. Let's say the probability of this is given to you, that it is given to you that disease is present. That means the patient is infected. So what is the probability of test is true? So let's say this is given to you, that is 0.9. Okay, 0.9 is given to you. And let's say this value is also given to you, that it is given that disease, the patient is not infected and test is positive. Let's say it is 0.2. Now, can you find out the remaining values, everyone? Can you tell me what will be the value of this one, second one? What will be the value of second one? Probability of test is negative. given that the patient is infected? Definitely it is going to be 0.1, because these two will sum up to 1. These two will sum up to 1. And what about this one? Again, these two will sum up to 1, so it is going to be 0.8. Is it clear? Any doubt, anyone? Okay. Similarly, let's talk about the symptom also, and then we will be solving this particular question. Okay. Now carefully see this. I'm writing here. So we have probability of S, symptom given disease. Carefully see this. So I can say that symptom is present. I'm just writing P, that represents present. Okay. Symptom is present given that disease is true. Let's say it is given to you that it is 0.95 maybe. Okay. And let's say other values are also there, whichever is positive. Like symptom is negative, symptom is not present, that means absent. Symptom is absent given that disease is true. Symptom is present given that disease is false. Symptom is absent given that disease is true. Oh, sorry, disease is false. Carefully see this. Let's say this value is given to you, that is maybe 0.1. Okay. Now, can we say that we can find the remaining probabilities? Yes, because these two will sum up to 1. Because it is given that disease is equal to true. Now, these two will sum up to 1. So if it is 0.95, I can say this is 0.05, right? And similarly, this is going to be 0.9 because these two will sum up to 1. Is this clear? So now, can you see carefully that now the CPTs are given to you? Yes or no? Can I say? Now the CPTs are given to you. Conditional probability tables are given to you. Okay. Now if I ask you a question, so in the GATE exam also, we will be solving one previous year question, and they have asked similar type of question. The graph, the Bayesian network that it was given in the question, that was a little different, but the way we are solving this question is going to be same. Okay. So now if I ask you a simple question, find out the probability that disease is present and test positive and symptom is present. Now how you are going to calculate this? So we have this now. How we can write this? Using Bayesian network only we have written this, right? Is it clear or not? So now carefully see this. So see, ideally, let me tell you one more thing. If you are wondering this, let me just tell you this. Let me add one slide here. Carefully see this, everyone. If I say probability of D comma T comma S, ideally what we should write, like using conditional probability and multiplication, we write like, right? Say probability of D, probability of S given, no? Do you agree or not? Yes or no? Okay. But carefully see here, what we can use here. We are using the conditional independence. Actually, we are using conditional independence here. That's what I told you, right? That Bayes theorem and conditional independence together, together form the concept of Bayesian network, right? So here, given D, carefully see this, given D. So D is given, that is given cause, effects are conditional independent of each other. So you can simply write like this, P of D into P of T given D into P of S given D. And this is what we have here also. Is this clear? So now are you able to relate how we are using the concept of conditional independence and Bayes theorem together? Crystal clear? Okay. Now this is the question that you have. Now how to solve this? So you simply know that it is nothing but probability of D into probability of T given D into probability of S given D. This is what you know, right? So what we want to find, probability of D is 2. That means you need to find probability of D is true, multiply probability of T is test is positive given disease is true, multiply symptom is present given disease is true. Now, can we substitute the values directly using this table? So can you tell me what is the probability of D is true? That is 0.8. Carefully see this here. That is 0.8. So I can say this is 0.8 multiply. Probability of test is positive given that disease is true. What will be the value here? Probability of test is positive given that disease is true. Can I set as 0.9? This value we will be using 0.9. So multiply 0.9. Then probability of symptom is present given disease is true. Symptom is present given disease is true. That is 0.9. And whatever value, can you tell me calculator and let me know what will be the answer? That this particular scenario. Yes, anyone? Just use the calculator or let me just use it. 0.8 multiply 0.9 multiply 0.95. It is 0.684, right? Yeah. 0.684. That is the answer. Is this point clear to all of you? Is this concept clear to all of you? Any doubt, anyone? If you have understood this now, then you can assume that you know what is Bayesian network. You can solve question based on this. Is this clear? Shall we proceed now? Just let me know once, everyone. Okay. Great. So the same thing is mentioned over here also. Fine. Now let's just give it a read. These statements are also important. We have already discussed, but let's give it a read. Independence simplifies the models, right? If two variables are independent, I do not need to model their interaction, but I can reason about them separately. What it wants to say here, carefully see this. Let's say I have some Bayesian graph like this. Now, carefully see this. Can you write the joint probability distribution now? Just give it a try in your notes. Don't tell me this. Don't tell me in the chat section. You can just give me thumbs up once you are done. Just try to write based on your understanding. Just try to write the joint probability distribution using the concept of conditional independence and Bayes theorem. Whatever we have learned just now. Just try to write it and let me know in the through your thumbs up. Do it. Is it done? Should I write it now? Yeah, that is correct. That is correct, Abhas. So carefully see here. Carefully see here. See A and B. So let's say if I'm starting with A, let's say. So because there is no incoming edge to A, so you can start with B also. It's up to you. So probability of A. Now A is independent of everything, right? So I can simply write probability of A. Okay. Multiply. What about B? B is also independent of anything, right? Everything you can say. B is not dependent. There is no relation between A and B, right? So direct relation you can say. So can I say both A and B, they are having absolute independence? Yes or no? So we know in case of independent events, we can write like this, P of A into P of B. Okay, what about C? What about C? C is conditionally dependent on A also. C is conditionally dependent on B also. Right? So in that case, you can say probability of C given A comma B. Is this clear? Or B given A, B you can write. That is correct. Is this clear? Any doubt here? So once you are able to write these things now, then you are done. Okay, you are done. Yeah, that is intersection. Yes. Oh, I missed that. So it should be intersection. Yeah, not union. Fine. Okay. What about this one? Can you tell me what will be the joint probability distribution for this one. Can you write it, everyone? Probability of A, comma B, comma C. Try to write it. So in the exam, they can give you a Bayesian network of 3 variables, 2 variables, 3 variables, 4 variables, even 5 variables. And more than that, they are going to give you maximum 5 variables they will go. Okay. So let's write it here. So probability of A, there is no incoming edge of incoming edge to A. So you can simply write probability of A multiply. What about B? B is conditionally dependent on A. So B given A. And what about C? What about C? So C is conditionally dependent on B. So directly you can write B. C is also dependent on A, but we talk about the direct dependency. So we are going to consider only B, not A. Is this clear? So it should be C given B. Any doubt, anyone? Crystal clear? Shall we proceed now? Any doubt, anyone? Okay, fine. So let's read these statements. So in this form of independence, when simple independence called marginal independence also, however, a variable will tell me nothing about another variable by design. There is another more useful form of independence which maintains the connection between variables, but at the same time breaks down the whole system in separate regions, conditional independence. This is independence used by the Bayesian network. So mainly Bayesian networks use the conditional independence. That is very useful for us. And what is conditional independence? Carefully see here. When two variables are independent, given a third, they are said to be conditionally independent. For example, of A given B intersection C is equivalent to P of A intersection B intersection C given P of B intersection C, which is nothing but, you can see that if C is given, so these two are conditionally independent, so we can write like this. Okay, two variables are independent given a third variable. So let's say this is the third variable, it is given, so these two variables are conditionally independent of each other. The same concept that we are using. Okay, so Bayesian networks uses graphs to capture these statement of conditional independence. So you can see how powerful these graphs are, right? They are telling you a lot of information. They are telling you what are the variables which are conditionally independent. They are also telling you what are conditionally dependent, right? And they are also telling you the variables which are completely independent, they are having absolute independence. So all these informations are given by these Bayesian networks. A Bayesian network is defined by a graph. Nodes are stochastic variables, links are dependencies. No link means independence given a parent. So for example, if you consider this particular Bayesian network, age, t-shirt and literacy, can I say t-shirt and literacy are conditionally independent given age? Yes, we can say so. So there are two components in Bayesian network, as I told you previously also, qualitative and quantitative. Qualitative means this graphical structure. Quantitative means assessment of the probabilities. So these are the two major components of the Bayesian network. Crystal clear? As you can see here, so given age, t-shirt and literacy are conditional independent. So you can just base it on the age, you can answer whether or not. Fine. So this is not a very good example, but yes, you can consider it. Okay. And what else? This decomposition that we are doing. Bayesian networks decompose the joint probability distribution with the graph of conditional independence. This is what we did, right? Therefore, the graphical structure factorizes the joint probability distribution like this. So if this is the graph given to you, if this is the Bayesian network given to you, then probability of A intersection B intersection C will be nothing but probability of C, right? Probability of C multiply probability of A given C multiply probability of B given C, because A and B are conditionally dependent on C. Is this clear? Any doubt, anyone? So this is the decomposition that we do. Now let's try to answer a few questions here. I'm giving you a few questions here. So before that, let's understand this Bayesian network. So burglary, I hope you know what is burglary. Chori hona, right? So here it is given that burglary can happen, yes or no. Earthquake, yes or no. That means true or false. And there is alarm, right? Alarm will set off or not. So we can say here that alarm is conditionally dependent on burglary, right? And alarm is also conditionally dependent on earthquake, right? So if you talk about if you talk about in simple words, basically it is saying that alarm will set off when there is a burglary happening. Okay. Similarly, alarm will set off when there is an earthquake also. Then in that case also alarm can set off. Okay. And this is a very famous example. Like most of the IIT professors, ISC professors, they uses this example, and most of the professors in foreign universities also they use this example. So this is a very popular example that we have. Now Bayesian network is given to you. Apart from that, so in Bayesian network you have the CPTs also, right? Conditional probability tables also given to you. Now if I ask you a simple question, let's try to solve that question. Okay, let me know what will be the answer. If I say find out the probability of burglary is false and earthquake is true and alarm is true. Can you answer this question, everyone? What will be the probability that burglary is false, earthquake is true, that means there is earthquake, and alarm will set off? What will be the probability of this particular event? Try to answer this. You can use calculator if you want. Okay, we'll see. Anyone else getting the answer? Okay, let's solve this now. Carefully say this. So based on this Bayesian network, this graph that is given to us, we can write the expression first. So probability of burglary is false, multiply probability of earthquake is false, because these two are independent, right? And then probability of alarm is true. So this, right? The case where, yes, we are considering the case where earthquake is true. Yes. So alarm is true given that burglary is false and earthquake is true. Correct? I hope it is visible. If it is not, let me write it clearly. Given that burglary is false and earthquake is true. Fine. This is what we need to find out. So what is the probability of burglary is false? That means there is no burglary has happened. What is the probability of that event? That is 0.99. So 0.999. Okay. What is the probability of earthquake is true? That is probability of 0.02. Multiply. What is the probability of alarm will set off given that burglary is false and earthquake is true? Burglary is false, so alarm will set off. Okay, burglary is false, earthquake, this case, right? This case, fourth row. Yes. So it is going to be what? It is going to be 0.29. Now if you solve this, that will give you the answer. So can you tell me what is the final answer that you are getting? Zero zero two multiplied by 0.29. Yeah, your answer is correct, Manjunath. That is 0.000579. So let's say if I want to answer till this point only, 5 decimal places. So I can say this is going to be my answer. Is this clear? Any doubt, anyone? Most of the time in the gate exam, they will, whenever there's some numerical answer type question, be careful up to what decimal digits they are expecting the answer. If they say up to 5 decimal digits, 2 decimal digits, 3 decimal digits, answer accordingly. Okay? Is it clear? Otherwise, you will lose the marks. Even after solving the question correctly, still you will lose those marks, 2 marks. Is this clear? Now, there can be, if you carefully observe, there can be many questions possible here. Yes or no? Now, you can just, as a homework, what you can do is, you can take all those scenarios. Let's say burglary is true, earthquake is true, and alarm will false. Alarm will not set off. So like this, you can have multiple examples and try to find out the probabilities based on that. Is this clear? Any doubt, anyone? Okay, fine. Carefully see this now. Now let's consider this case here. So preliminary choices of nodes and values. Lung cancer example, it is given now. So we have these nodes: pollution, smoker, cancer, dyspnea, if I'm pronouncing it correctly, dyspnoia, X-ray, and their types are also mentioned, like binary, Boolean, binary, like this, and the values are also present over here. Now let's read this particular graph and you will understand that how they are making this Bayesian network. The structure or topology of the network should capture qualitative relationships between variables. In particular, 2 nodes should be connected directly if one affects or causes the other, with the arc, that means the edge, indicating the direction of the effect. So in our medical diagnosis example, we might ask what factors affect a patient's chance of having cancer. If the answer is pollution and smoking, then we should. So these questions you have to ask yourself. In the exam, they will definitely give you, but as an analysis purpose, you should ask whenever you are dealing with any problem statement, right? Then you have to ask what affects what, right? So in that case, so as it is mentioned, we might ask what factors affects a patient's chance of having a cancer. So if the answer is pollution and smoking, then we should have edges from pollution and smoker to cancer. Similarly, having cancer will affect the patient's breathing and the chances of having a positive X-ray result. So we should add edges from cancer to dyspnea and X-ray also. So after considering all this, this is the Bayesian network that we are going to come up with. There can be other possibilities also. It's not like just this Bayesian network is possible. No, you can have other things also. You can have other possibilities also. Is it clear? Based on what you are considering, based on your understanding, what can affect what. Okay, but it should be quite, it should be logical also, right? So this is what I want to say. Okay, so this is the Bayesian network they have come up with, and now they have given you this complete Bayesian network, where we are having the graph also, dependency graph. Apart from that, we are also having what? The CPTs, the conditional probability tables. Now, if I ask you, let's say I'm asking you again one more question. What is the probability? What is the probability that cancer is true? What is the probability? First, okay, before that, just try to write the expression for this, the joint probability distribution expression. Can you write it? Do we have it here? Just try to write the joint probability distribution. Then we are going to solve the question. So here we have 5 nodes here. That means 5 random variables are there. So you need to write what is the probability of cancer. What else we have? Let's say C, P, S, X, and D. And once it is done, just let me know. Then I'm going to write it and you can match. Is it done? Yes or no? Okay, do it. No idea. Why, Manjunath? It is simple, right? Just step by step, consider every random variable. You will be able to write it. We have seen how we can write it for 3 variables, right? Okay, let's do it now. Carefully say this. So let's start from maybe pollution, because there is no incoming edge. You can start from smoker as well. These two are completely independent. So I can say that probability of P, that is pollution, multiply probability of S, correct? Then what about cancer? So you can see cancer is conditionally dependent on pollution as well as smoker. So we can say probability of cancer given pollution and smoker, multiply. What about X-ray? X-ray is conditionally dependent on cancer. So we can write X-ray is conditionally dependent on cancer, multiply probability of dyspnoea, that is one of the symptom, is conditionally dependent on cancer. So we can say here that, let's say D given cancer. Is it clear? This is what is going to be the expression using Bayesian network and conditional. Mainly you can say the Bayes theorem and this concept. So this is what we are going to have. Now we can directly use it. Let's say if I ask you a simple question, what is the probability that cancer is positive? Okay, so yeah, so we can say what is the probability, let's say, so here true false is there, right? True false and high low is there, right? Pollution and X-ray, there is high low and positive negative, rest all is true false. Okay, so what is the probability that cancer is true? Pollution is low, smoker is true, let's say false, X-ray is negative, and dyspnoea, that is one of the symptom, that is true. Can you answer this? Just write this expression in your notebook, and then I'm going to show you these tables. Or let's do it now only. So carefully see this. What is the probability of pollution? Carefully see this. Probability of pollution low. So we are talking about, we are interested in probability of pollution is low. So we can say probability of pollution is low, that is 0.9, multiply. Probability of smoker is false, because here we have this, right? So we are going to consider that particular value, that is smoker is false. Smoker is true is 0.3, that means false is 0.7. Then probability of cancer given pollution is low and smoker is false. Pollution is low and smoker is false. That is 0.001. 0.001. Then what is the probability of X-ray is negative and cancer is true? X-ray is negative and cancer is true. Now, can you tell me the value here? X-ray is negative and cancer is true. Can you tell me what will be the value here? Just focus on this CPT. We want to find that X-ray is negative and cancer is true. Let's see if you can tell me the correct value or not. Exactly. Very good. That is going to be 0.1. 0.1. Why? Because see, we have this expression, right? So this given true. So when this given true, then X-ray is positive is 0.9. That means when X-ray is negative is going to be 1 minus 0.9, that is 0.1. I hope it is clear. This thing I've already explained it to you. So point 1 is there. Now, what is the probability of disease, the symptom dyspnea is true given cancer is true? This value 0.65 only, right? 0.65. So once you solve this, that will give you the answer. Is this clear how we are solving these questions? The first important thing is carefully observe this Bayesian network. The second thing is write the joint probability distribution expression correctly. And the third one is just substitute the values, whatever is required. And then you are done. 2 marks in your pocket. Is it clear? So here also they have mentioned the same thing, that we are using the chain rule of probability and we are writing this and then multiplication of probability x given parents of xi. That means if parent is existing, then you can say child is conditionally dependent on parent, right? If parent is not there, then you can simply write the probability of that particular node, right? Probability of random variable having certain value. So carefully see this. This is what we have written. So this was our Bayesian. If they say is positive and D is true, C is true, pollution is low, smoker is false. In that case, after just after considering that conditional independence and everything, this is what you are going to get. And this is, you can verify the same thing we have written. Probability of P is low. Just forget about what is the value of certain random variable. Just focus on probability of pollution into probability of smoker, right? Multiply probability of cancer given pollution. So cancer given pollution and cancer given smoker. So can see basically cancer. Okay. Have we committed mistake here or not? Yeah, that is fine. We have also done it right correctly. Cancer given pollution and smoker. This thing. Yeah, that is also correct. Fine. So this is what we are having, because cancer is conditional dependent on pollution as well as smoker. So pollution probability of cancer given pollution and smoker. What about X-ray? Probability of X-ray given cancer, because X-ray is conditional dependent on cancer. So which is here, and probability of the symptom given cancer, which is here. Is this clear to all of you? And now based on the values of these random variables, you can substitute those values and you can find out the final answer. Okay. And this is, as I told you, this is a very famous example that we have. Considered the following 5 binary random variables. B stands for a burglary occurs at your house. E stands for an earthquake occurs at your house. A stands for the alarm goes off. J stands for John calls to report the alarm. M stands for Mary calls to report the alarm. Now suppose we want to answer queries like this. Probability of B given M comma J. That means probability of burglary has happened given that Mary has called and John has called to report the alarm. Suppose this is what we want to find out. And this is the Bayesian network given to you. So what you will do? What you will do? If this is what you want to find out. If this is what you want to find out. Then in that case, it is, you can write like this: P of P intersection M intersection J divided by P of M intersection J. Or you can also write like this, that you know this is what the total probability is. So we can write BMJ divided by probability of BMJ plus probability of not of BMJ. Yes or no? Do you agree or not, everyone? This thing we can find out. We know this, that using this concept of Bayesian network, we can find this joint probability distribution. This is the same thing. And similarly, we can find this also, where burglary is not, burglary has not happened, and then these conditions are there. So can I say I can answer any queries? Yes or no? Yes or no? Okay. So if this is given to you, you can find out. You can find out all these things. Okay, let me just ask you a simple question. Can you answer this? What will be the probability of burglary has happened and let's say John has called then let's say Mary has not called, alarm goes off, that means true, or sets off, and earthquake has not happened. Can you answer this? So I want you to practice again and again so that it will be very easy for you to answer these type of questions. Quickly answer this. First of all, what you need to do, you need to write the expression based on this Bayesian network. Once you write the expression, substitute the values, get the answer. So I'm writing the expression here. That is going to be what? Probability of burglary is true, multiply probability of earthquake is false, multiply probability of alarm given burglary. So let's say alarm is true, given burglary has happened and earthquake has not happened, multiply probability of John has called, given alarm goes off, multiply probability of Mary has not called, given alarm goes off. Yes or no? Have you written the same expression? Just verify. Probability of B into probability of E into probability of A given B and E, multiply probability of J given A, multiply probability of M given A. Yes, that is correct, Abhas. So once you know this, now you can just substitute the values. Quickly do it and let me know the answer, the final answer. Because it is also important that you should have a habit of finding the values from the table also. Do it. I'm giving you 1 minute of time. Or let's take 2 minutes of time, but do it correctly. BE table is not visible. A given BE. Okay, this is true, 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 false, false, true, false, false. Fine now. True, 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 false, false, true, false, false. Is it visible now? I'm sorry. Do it. Is it done? Everyone? Okay. So now what you need to do, you need to just substitute the value here. So I'm just substitute the value here. So probability of B given true, burglary has happened, that is 0.01, 0.001, right? As you can see here. Probability of earthquake has not happened, that is 0.999. You can just verify your answer also. Probability of A given true, probability of A is true given B is true, E is false. B is true, E is false. Second row, and A is true. So 0.94, yes, 0.94. Probability of J is true and given A is true. Probability of J is true given A is true. That is 0.9. That is 0.9. Yes or no? Probability of J is true given A is true. So given A is true, this one. Probability of J given A is true, that is 0.9. Correct. Then probability of Mary has not called, given alarm goes off. Mary has not called and given alarm goes off. So A is true and Mary has not called. That means 0.3. So into 0.3. This will give you the final answer. Is this clear? I think Abhas, you have made one mistake. It should be 0.9 instead of 0.05. Is this clear? Any doubt, anyone in this? This should be the answer. Okay. Fine. So all these things we have discussed consist of DAG, directly or cyclic graph, and a set of conditional probability distributions. You know what is DAG? I have already explained it to you, so you can just give it a read here. As you can see, the same expression we have written, right? And it is having 32 parameters. So basically, this is also having two possibilities, right? So 2 into 4. This will be having how many possibilities? So basically, total will be 32, right? If you don't use the concept of conditional independence and independence, then you can say total 5 Boolean variables are there. Every variable is having 2 possibilities, so it is going to be 2 raised to the power 5. That is 32 parameters. But if you want to reduce it, so you can say the Bayesian network representation of this distribution will have 20 parameters. How? 2 here, 2 here, right? So here we are not using the concept of like 1 minus that thing, because if you're using that, you can further reduce it. Okay. So here it is going to be what? It is going to be, this is 2, this is 2, this is going to be 4. Okay, just a minute. This should be 4, right? Not 2. 8, 4. Yeah, this should be 4 here. So basically, if you talk about this burglary, it will have how many parameters? So it is independent, right? Yeah, it will be 2 here. That is correct. That is correct. And what about alarm? So alarm is conditionally dependent on burglary. Alarm is conditionally dependent on earthquake also. So it is like this: alarm given burglary and earthquake. So how many parameters? 8 parameters, right? 8 parameters will be there. Correct. And what about this one? 4 parameters here and 4 parameters here, because this is what this is: probability of John given alarm and probability of Mary given alarm. That we have already seen. So 4 parameters here, 4 parameters here, and 8 parameters here. So total how many? 4 plus 4, that is 8, 16, 20. So 20 parameters will be their total. So it may be possible that sometimes they may ask you a total number of parameters possible also, given a Bayesian network. Okay. For example, if you see this one, how many random variables are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? And let's say all are having, so 10 binary random variables are there. So 2 raised to power 10. So ideally it should be 1024. But what about this one? Here, this is having 2 parameters. This given this, so 4. This given this, so 4. Similarly, 4, 4, 4. Same scenario. 4 here, 4 here. But this one, it is conditional dependent on these 2. So it should be 8 here. So total, if you add, it will become 42. So this is one of the, you can say, one of the possible question that can be framed. Okay. So this is important. They have not asked this type of question because just one time gate day has happened. and they have asked the question that we have already solved, similar type of question. But this type of question is also possible this time. What are the advantages of Bayesian network representation? It captures independence and conditional independence wherever they exist, encodes the relevant portion of the full joint among variables where dependencies exist. So where you have actual dependencies existing, it considers only that relevant portion in the full joint. It does not consider everything. Uses a graphical representation which lends insight to the complex of inference. So we can basically inference from that particular graph. Again, the same thing that we have already seen. So yeah, same example, nothing changed here. As I told you, you can calculate this, right? You can compute this thing also by this. So you can calculate this thing, this is same, and similarly you can calculate this also. So you can answer anything. Now I want you to answer this. Yeah. This is the question. This is the GATE 2024 question based on Bayesian network, and it was asked for 2 marks. So I want you to try, everyone. I hope it is visible to all of you. Start doing it and let me know the answer. And let me tell you one thing, like what I feel is from Bayesian network, they are going to ask you question every year. Like one question will be there for sure from this topic. So once you have understood this clearly, then you can answer these type of questions easily. The first task should be writing the expression for the full joint probability distribution and then substitute the values. Anyone else getting the answer? Yes, that is absolutely correct. Very good. So here we need to write the full joint probability distribution. We can write like, see, let's see question also. Consider the following Bayesian network consists of 4 Bernoulli random variables. That means they can have 2 possible values, each random variable. And the associated conditional probability tables, CPTs, are also given. You can see here, right? Now we need to find what will be the value for this one. So where U is probability of U is 1, V is 1, W is 1, Z is 1. Now you can simply write probability of U is not dependent on anything. So probability of U multiply by, what about V? Probability of V given U multiply probability of W given U multiply probability of Z is conditional dependent on V and W both. So V and W, right? So basically this should be 1. Here V should be 1, U should be 1, W should be 1. So everything should be 1. So I'm not writing it, but yeah, you understood, right? Because here everything should be 1 as it is given in the question. So directly you can substitute P of U when U is 1. That means this thing, that is 0.5. Probability of V given U when V is 1 and U is 1. So when V is 1 and U is 1, 0.5. See, if you focus in the CPTs, they have mentioned every value, right? But if they don't mention, then you can find it out also, right? 1 minus the other value, you can find it out. So maybe the next time they will frame that type of question. Like they will make it a little more complicated. Not complicated exactly, but yet, but yes, I can say some of the students can commit silly mistake also. So be careful of that. Multiply by probability of W is 1 and U is 1. Probability of W is 1 and U is 1, that is 1 only, right? And probability of Z is 1, V is 1 and W is 1, that is 0.5. So it will give you what? This is 125, so 0.125. And there you have to answer rounded off to 3 decimal places. So yes, that is your answer. Is it clear? Any doubt, anyone? Simple, right? And this question was asked for 2 marks. Now I'm giving you some homework related to this Bayesian network that you can do. Simple homework. What it is, draw the Bayesian networks for this joint probability distribution for all these parts. So based on this expression given to you, yes, now you can get I can tell you, like, after attending this lecture, anyone can get 2 marks from this Bayesian network for sure. And definitely there will be question. Definitely there will be question from this topic. Okay, so you have to make the Bayesian networks, draw the Bayesian networks for all these. And this is very simple, just based on the dependency. You can understand from which node to which node there will be the edge and where it will not be. Okay, so do this question. And this question again, this is a very nice question that is taken from IIT Kharagpur, I think mid-sem exam. So just read this question. You will enjoy solving this question also. Not a numerical question, a simple joint distribution you have to write. You have to draw the Bayesian networks. That's all. Okay. Yes, P or alphabet distinguish nahi ho rahe hain. Where? Okay, here. No, P is definitely, it would be right. P is probability, right? You don't have any variables here named as P. Abhas. Only A, B, C, D are there, right? So you will be able to differentiate. Fine. And try to solve this question. This is very simple question, but yeah, this will help you to, sometimes, yeah, one more thing I wanted to mention here. It may also happen that this time, if they give you a question based on Bayesian network, it may also happen, instead of directly writing these values, they may give you some statement also. Like if you consider the example of burglary, they may give you some statement like this, that find out the probability of burglary has happened and there is no earthquake that has occurred at your house. Also, it is mentioned that alarm goes off when John has called but Mary has not called. Understood? So based on this statement, you have to find out the values and then you have to solve the question. Is this clear? So instead of directly giving you the values of the random variables, they may give you the statement also. From there, you have to find the values and then you have to substitute. I hope it is clear to all of you. So just to make it a little more not complicated again, just a one level above, they can make that question like this. So try to solve this question and you can discuss the answers in the in the WhatsApp group, okay, for AI, or maybe in the Telegram group, okay, so that you can find out the correct answer also. Fine. I will create it. I will create it just after this class. I will create one WhatsApp AI group. There you can discuss. Fine. And these are the questions in continuation to it. Clear? So I hope you enjoyed it. Is it clear to all of you? Tomorrow topic, we will be talking about Markov model. So Bayesian